Well, thank you for nice words, and thank you for the invitation to come here. Yes, the theory of positive maps really started with Caddison in around 1950. And one of the motivations was that first of all, a positive map is the one that carries positive operators to positive operators. And I stated for C-star algebras, but you can just as well think. And during the lectures, I will just matrix algebras. And it was more, if such a map takes one-to-one, if you compose it with a state, it's still a state. So this composition defines an affine map on the state space. So in that, it was somewhat inspired by quantum mechanics when they did this. And Caddison showed this famous inequality that for self-adjoint operators, you have that phi of A square is square of phi of A for such maps. But we'll limit ourselves to maps of the n by n matrices into themselves, because notation becomes a little simpler, and we'll usually do this theory in finite dimensions. You see, the history of the subject was that very few people worked on this subject until the 1990s, when people from quantum information theory got interested in the subject. Then they exploded. Now there are lots of people doing it. And many of the problems were of the type that you had some kind of physical problem, they formulated it as positive maps, and then they proved the results that was related. I have sort of tried to make a theory out of it, and then that's the cones will appear. But there are three kinds of maps that are most known, and the work has been done mostly with. They're the so-called superpositive, or physics usually call them entanglement breaking. And they are the form you take a sum of the form that AI is positive operator and omega is a state. They are the nicest maps. And then you have the so-called completely positive maps, which for the n by n matrices is just those for which the identity map tensor phi is positive on the tensor product of MM by itself. In general, you define complete positivity that the identity map on any n by n matrix tensor phi is positive. But here we need only the identity. And then you have the so-called decomposable maps, which are sums of the form phi is equal to alpha plus beta, composed with a transpose map, where alpha and beta are completely positive. So these are the nicest maps you come across. So one of the main techniques in this subject is the so-called, when you use the so-called Choi matrix. It is, you take matrix units, Eij, of the n by n matrices. Those are the matrices with 1 in the ith stage, Ij placed on the matrix and 0 everywhere else. And then the Choi matrix for phi is C phi, which is sum of Eij tensor phi of Eij. So these can be looked at as block matrices. The Ij block is phi of Eij. So you see, you can go back and forth. If given a matrix, you take the blocks and you define phi by that. So this is an isomorphism called the Jamjolkovsky isomorphism by people in the subject. And so what we'll discuss much of in this lecture is that the relationship with C, phi, and phi. You see, this reduces the study of maps to the study of matrices in the tensor product. And this, if you look at write this out to take one, the identity tensor phi, apply this to P, to the one-dimensional projection P on this vector EI, tensor EI. Then it's a very simple form. It's just the application to one matrix, one-dimensional projection. And this projection is on this vector, and that is separating and cyclic for one tensor Mn. So if you apply this one tensor Mn to the vector, you get all of the tensor product of Cn, tensor Cn. I'll skip this part because. And the main theorem of Choi was that phi is completely positive if and only if this operator C phi Choi matrix is positive. And you can show that this is the same as saying that phi is the sum of maps of the form add vi, and add v of x is v star xv. So it's a standard. I forgot to write that on, but that will always. These are very central then.
Is this a result for general systems or for matrix?
No, this is true for general, but I'm sticking to the simple one. So now you see some of the basic properties of this Choi matrix. So you take the usual trace on Mn. Then you have that phi is positive map, written phi is equal to 0. If and only the trace of C phi times A tensor B is positive whenever A and B are positive. That's a characterization of positivity. So you see we have a positive on a very restricted class of matrices. And phi is completely positive, that I said up here, if and only C phi is positive. And that's if and only C phi trace of C phi x is positive for all x positive, because each positive matrix is the Choi matrix of a completely positive map. And it's super positive, then you see it's quite strong. It says that trace of C phi, C psi is positive, all psi positive. That is a very hard thing. And you see, these characterizations are not easy to check because you have to check them on all possible conditions here. So this is a handicap of much of the theory here, that you have to do it for all, and that's very hard to check in practice. And then if you have a mapping, you can define a linear functional on the tensor product called the phi tilde. And you define it on tensor products because they generate the whole algebra. By phi tilde of A tensor B is trace of phi of A B transpose, or equivalent to trace of A phi star BT. Phi star is adjoint. You look at this as a Hilbert-Schmidt problem, so the phi star is just the adjoint. In that sense, as the Hilbert space operator. Consider phi as an operator on the Hilbert space. So this, and then you have a very, you see, this is quite nice. You have it. You have you have a map. You have a matrix, and you have a linear functional. And you compare all three of them in different situations. So the theorem that sets the properties of phi tilde, first of all, its density operator is a transpose of C phi. So you have a very close relationship. When I say density, I mean include non-positive maps. There's a Radon-Nikodym derivative with respect to the trace. And you have that phi tilde is positive if and only if phi is completely positive. So you have a state, so each completely positive map corresponds to the state here, up to scalar. And phi tilde is separable. That means that the sum of tensor products of states, so sum of product states. That's if and only if it's separable. And that is if and only if he is superpositive, which is very strong. And that's if and only if C phi is separable as a matrix. That means it's a sum of AI tensor BI with AI and BI positive. And that's a problem here. It's a very difficult problem, which is unsolved. To given a matrix in Mn tensor Mn, show whether it's separable or not. That's a hard open problem. So it's it's not obvious, these things as they may look. So I'll use this notation during this lecture I'll use the notation P for a set of positive maps, CP for completely positive maps, SP for superpositive maps, and co-CP for so-called co-positive maps, phi tilde, phi composed with a transpose map. So these are the central maps here. So, yes. I forgot to say one thing about this result here. It's sort of interesting. This one, of Choi. He told me this has been referred. He told me it had been cited more than 2,000 times in the literature. It's amazing that almost everybody writes about the subject quotes that paper. So now I go to the cones. You see, I wrote a paper in '86, where I tried to make a theory out of a general theory for positive maps, where I decided that they could put them into cones of different types. So I defined what I call the mapping cone. That's a closed convex cone in P, such that if you compose on either side by a map phi, but completely positive maps, they're still in the cone. And the reason for doing this was that completely positive maps are easy to discuss, or because you correspond to checking that this Choi matrix is positive, which is not a hard problem. So that's why I call them mapping cones. And the typical examples are all these three cones I have up here. And if you take the cone generated by CP and the co-CP, then you have the decomposable maps, because they're a sum of one completely positive and one co-positive. And the superpositive maps, that's the smallest mapping cone of all. As you will see, if you have of course, if you compose a state, either on the front or the back by a positive map, it's still positive functional. And so on. And it's easy to show that they will generate. All of them will be inside any cone. And I will always assume the cones to be symmetric. That's at the adjoint map of phi, as I defined it earlier, is there. And also if you compose by the transpose, both in front and behind, it's still there. This is important for the theorems to be used, that I have this assumption. And as you have, for example, in Hilbert spaces, if you have a cone, then a dual cone is the set of vectors that have positive in the product with the elements in the given cone. And you have to use the same definition here. The dual cone, J naught of J, is a set of maps such that trace of C phi, C psi is positive for all psi and J. That's the same as the in the product, you see. And you get since it's close, you get that the second dual is equal itself. And examples are here. All these, a dual cone of P of all maps, that's the smallest cone, that's SP. And the dual cone of SP is P. And the dual cone on the completely positive maps is the completely positive maps itself. So here's a characterization of the dual cone. Take a mapping, take phi positive map phi and J a mapping cone, and all following 5 conditions are equivalent. That phi is in the dual, and here comes 1 alpha, tensor alpha, or C phi is positive for all alpha in J. Phi tilde, composed with identity tensor alpha, is positive for all alpha, and alpha composed with phi is completely positive for all alpha in J. That's a sort of strong condition. And the tensor product the same. And you see again, it doesn't really help you to show that something is in the dual cone. Yeah?
Is the dual the original cone?
Yeah. Whenever it's closed. Yeah. So you have to do it for all alpha. So it's, for practical purposes, not very useful, but shows in theory you get it. And there are applications I will do also. I'll just to show you the techniques, I'll indicate the proof of parts of it. Take that equivalence 1 and 2. So phi is in J naught, if I know trace of C phi C. And I write every element in J as alpha composite psi for all psi, because you can just as well have compositions. And then what is C of alpha composite psi? That is the same as 1 tensor alpha of C psi. If you remember the definition, you find that tensor EIJ is tensor phi of IJ. That was to have a composition, you take the, like here, you get 1 tensor phi of I. Oh, you see, so the Schroedinger matrix of phi of alpha composite psi is 1 tensor alpha of C of psi. It follows immediately from the definition. And then you can take the adjoint over on the other side. And then this is for all completely positive maps. So that means that this operator is positive. And that means that 1 tensor alpha is positive, of C of phi is positive, because it's symmetric. So that's just one more. So this shows very many computations are of this type. And 2 equivalent to 4, to have that C of alpha composite psi is, as I said, 1 tensor alpha psi. That's positive for all alpha if and only if this is positive for all alpha, because that shows it's completely positive. So that is one thing. But there's one stronger kind of mapping cones that comes into the picture, which is they're somewhat bigger than the other ones. I say it's invariant, a mapping cone. It's not only that composed with completely positive maps is still in the cone, but you compose with all positive maps is still in the cone. That's it's difficult to check, but that is it has some nice properties. As you see, you can improve the previous theorem as follows when you have this condition. It's invariant. Then all the conditions I had are equivalent to alpha composite psi with phi is super positive for all alpha and j. Or you can compose the opposite order. And that's if and only if alpha composite psi is separable, tilde is separable for all. So that is, in a sense, quite strong, very strong result. And so that one cone, you take a composition, one dual, and it's super positive. It's very, and that's it. You see, it's that you compose and take the tilde, it's separable. So you get back to separable. So you have a cone and the dual cone, then you get separability of them easily. And I can just indicate the proof. You have alpha and j, psi positive maps, then alpha star composite size and j by assumption. And then C phi of alpha composite psi of C psi is the trace of C psi alpha star. Yeah, you take alpha from here over there. And then you see that left side is positive for all alpha if and non-live. Let me see. Left side is positive for all psi, all positive maps. If and non-live, this one then is super positive. Until it's on the right side. So you have this strong result that phi is in the dual cone if and only alpha composite size separable for all alpha and j. But as I said, most of these results are for all alpha, which makes it difficult. But here is one that does not require that. Take a corollary. You take an invariant cone, and you take the maximal rank you can for a projection in the cone. So add p's in the cone. And mapping x go to p, a, p is in the cone. And assume map k is greater than or equal to 2. Then if you take phi in the dual cone, and the rank of the range projection of phi is less than k, then phi is already superpositive. Or if you have a projection in n by n matrices, and the rank is less than or equal to k, then it's already RE already in J. And here is shows some of the techniques the previous result use. So you choose a P such that is satisfied, so rank is P. Then you take the range projection here of phi, it's F. Then F is equivalent to a subprojection of P, because the rank is smaller. So there finns a partial assumption moving one to the other, P into F into P. So you may as well assume that F is less than P, because you use the property of the cone to get. But then you see that add phi is equal to add P, because P is equal to F. Compose with add phi, add F. And F is in J. No, F is, add P is in J. And phi was in J naught. So, yeah, that should be a phi, isn't it? Yeah. So that's add phi is, add F, excuse me. No, add P composed with add F, yeah. It's in J because P is in J. Right? Add F is add P because composed with add F because P is smaller than P. And then you have that phi is equal to add F composed with phi because F is a range projection. Now add F is in J, phi is in J naught, the product is in superpositive. So that's a way to show that maps are superpositive. The last one is very easy. That's the same argument as you have here. There's one cone that is quite, at least when I do in this discussion, it's quite important. That's call it D2. Then you take the cones generated by all alphas on all projections E, such that E has rank less than or equal to 2. All such projections take generated. And that is by the argument I had is that you can just take one projection and still get the same cone. But then Now interesting is that you take the dual cone of this cone, D2, take any projection in there, add E is in there, then it's already superpositive. So you have excluded add E from the cones. And well, if it's less than or equal to 2 rank, then you know by the previous result that it's already superpositive. If it's less than 2. If rank is greater than 2, you choose a projection smaller than it of rank 2. Then add F is in D2 by definition. And then add F is add E composed with add F. And that's superpositive because the product of one from D2 and one from D2 in a dual. So you get add E, any sub-projection is in SP, that means itself is SP. Or, okay. So that's enough about the general theory. Now I'll talk about the class of states of maps, which you may have heard about, the PPT-states. They were introduced by Paris in 1996 or something. They're called positive partial positive transpose, or positive partial transpose state. And there are such that the identity tensor transpose is not positive map. Transpose is not completely positive. So you have composed a state where it's still a state, so that's a strong condition. And these maps were then introduced in order to hopefully have a characterization of separable states. But Pavel Horodeski showed a year later that there was a counterexample to that. So, but they're still looked at. So for simplicity, I did of this lecture call phi a PPT map if phi tilde is a PPT state or a scalar multiple of 1. So then you have some equivalent conditions for a map to be a PPT map. The equivalent is that it's both completely positive and completely positive, both of them at the same time. Or another equivalent condition is that phi composed by alpha is completely positive for all alpha in all decomposable maps. That's a union of those two cones. And I'll include the proof of 1 and 2. Both of them, I will conclude the proof. So you look at phi tilde composed with the identity tensor T, you want that to be a positive map, positively functional. And then you have to check it on A tensor B. And then you get, by definition of phi tilde, that is phi tilde of A tensor B transpose, because you have transpose here. And that's, by definition of the phi tilde, trace of phi of A, B, because you have the transpose when you defined it. But the trace is transpose invariant, so you can take T on both B and T, phi of A. And this is equal to T composed with phi of tilde of A tensor B. And then you see that phi tilde is PPT if and only if both phi and T composed with phi are completely positive from that. Excuse me. It's a positive, yeah. So you have that phi if and only if, phi tilde was positive if and only if phi is completely positive. So that's why we get conclusion here. So again, you have this result that you want to know something, and you have to assume it holds for all things than the alphas. So I will give another argument for the last condition here. What happened? Okay. So we have, as for usually for cones, the dual cone on the intersection is the generated cone by the two cones. That's a very common thing for cones, closed cones. The dual cone of the intersection is a cone generated by both duals, which is the union of the duals. And then you had by the first theorem that phi is in this intersection, that this PPT. That means that the intersection is the dual of the generated cone, and that means that phi composed with alpha is completely positive if and only for all alphas in the generated cone. That was the characterization we had about the dual cone. There is one Voronovich in the early 70s showed that maps from M3 to M2 or from M2 to M3 are positive, then they are decomposable already, automatically decomposable. This is not true if you replace 2 by 3 here, but 2 to 3. So in particular, if you have a mapping from N3 to M3, which is positive, and you have a projection of rank 2, then add E composed with phi or phi composed add E are both decomposable because they are essentially, you can add E that goes into 2 by 2 matrices. So now I look at this from now on. I really look at only at 3 by 3 matrices, n equals 3. You see, this is the only case where you can really prove something. So we take phi a PPT map and n equals 3. Then automatically phi is the dual cone of D2. That is the cone generated by 2 by 2 rank 2 projections. And that's the same as saying that phi composed with alpha and alpha composed with superpositive for all alpha in D2. That's by this early theorem. It's a dual cone, and in the cone, so you know if you have a phi, it's in here, and you compose with phi in D2, it's superpositive. And also, if the range of phi or the support of phi is a projection of rank 2, then phi is superpositive. So this follows from the previous results. D2 is composed subset of that one because they're all sums of completely positive and co-positive, and that's same as the dual cone of the intersection. So therefore, phi is in D2. Oh, excuse me. Yeah, and therefore phi was already in the intersection, which is the dual cone of the generated cone. That's D2. That follows from Voronovich. And these other two follow from the previous theorems we had. So this was used also by, I think, Pavel Horodecki to show that a similar thing, if you translate this to phi tilde, he proved some very close result to this. But the interesting thing here is that these results are special, fall from general theory of the cones. So now I'll discuss, you see, as I said, they're very difficult to study special maps, because if you write up a map, what it does, it's hopeless. You get this Troy matrix is a big matrix, and from there, what can you deduce by just knowing the coordinates? It's not so easy. But there are some maps which have been studied in detail, which were constructed as counterexample candidates for counterexamples. And that is by Ha and K and Osaka. You take positive numbers and an angle, theta, and you have a matrix, Xij and M3. Then you define a mapping phi of A, B, C, F, theta of X. I normalize it and divide it to this, so the identity goes to the identity. And it looks like this. You have sort of permutations of the diagonal elements. And you multiply each coordinate by this unit complex number of norm 1. And Choi first studied a map. This is based on Choi's map from 1880. That's phi of 1 tends to 1, 1, 0, 1, 1, 0. That was the first example of a map which was not decomposable. And if you look at the identity map, then you let the angle be pi, then you get plus 1 every place here. And you get this AX1, that's A is 1, B and D is 0, here you get X2, and here you get X3. So it's identity map. And some maps you want to exclude completely positive maps. Inside should have no summand of completely positive maps, or rephrased. Does not majorize a completely positive map different from 0. They are called optimal. And introduce a number here which depends on the angle. It's not important to what it is. And then Ha and K showed in 2012 that this mapping is positive if and only if you have two conditions. These numbers are bigger than that number, and BC is greater than or equal to that, 1 minus A squared. And if both map is a positive and P between 1 and 2, this mapping phi is optimal. If A is less than 1 and B, C is equal to 1 minus A squared. So that is just a condition, and the proofs goes over several pages. It's quite delicate estimates. It's not important the reason why I state this theorem is that I need it in a second. You see, if you take now you have a general positive map, and you assume it takes 1 to 1 for simplicity, like I just defined, the ones I defined. Then you take the convex combination with the normalized trace, phi t. So that the point is here, you want to approximate phi by some maps of this type. And it's a well-known result that if, for example, T is, you have the T is small enough, then it's separable automatically, or superpositive, I mean. So in one way, you try to approximate by superpositive maps, or weaker for bigger T for completely positive maps. And if you take the Troy matrix of the trace is 1 tends to 1. So you get the system. So the convex sum of this. And you choose the largest T star, such that this map is positive. So phi t is completely positive. Take the largest one. So that means that it's the closest completely positive map in the direction of the trace. And they define the SPA, or the structural physical approximation for phi. That's the Troy matrix of phi t star. And when this was introduced by, you may know the names better than I do, Koivish, Almeida, Bar, Levenstein, Eisen, you know the names? From quantum information theory people, I guess. And they checked lots of examples. And they thought that, it's always separable, this one. But the problem is they checked all the examples they knew were always nice maps. So they got the right result they wanted. So they conjectured that it was always separable. But both Ha and K and I studied these things independently. And they beat me by a month to show that there's a counterexample. And the counterexample all were from this class I defined. Just this. So then you have n equals 3. And as I told you, the identity map is this, phi of 1, 0, 0, pi. So now you choose, I just have the theorem here. I have the theorem here. So you choose A very close to 1, B and C close to 0, and theta close to pi. So you have this holds. And then you see that so this is close. This will be very close to the identity map in that case. But and the SPA map is continuous. It's very easy to see. I can even show you why in a second. And yeah. So it's so by continuity of SPA, this mapping phi is close to SPA of the identity. But the problem is that the identity map is very far from being superpositive. You see, one way from what I said today is because if the identity map is in a mapping cone, invariant mapping cone, the mapping cone is all positive maps. And you can't expect that to happen for the identity map for all mapping cones. So it's far from being separable. If it was separable, if this is SPA identity was separable, it would be superpositive, which is far from being that. So, by continuity, since SPA phi is far, so then, since SPA of the identity is far from separable, the SPA phi will also be far from separable. So, that's it. I think this is a good time.